Yes, yes, yeah. We have to call people. Oh, excellent. Yes. This live streaming is not. Okay, guess I'm audible. Good morning, everybody, and welcome to IIT Gandhinagar. Welcome to the third edition of IndoML, in the Indian Symposium on Machine Learning. So I'll just say a small, only a brief set of words, and then I'll invite Professor Amit Prashant, our Dean of Research and Development, in order to inaugurate the symposium. So just some stories about how IndoML started. Right? I mean, there's a popular saying, right, possibly originating in political circles, that says that never let a good crisis go to waste. Okay? I think that perfectly captures how IndoML started, right? It was the sort of the COVID was starting out, and then we were all homebound, and we decided what to do, right? That we wanted to have some activity to engage people in, right? And from this core group started from IIT Gandhinagar as well as from IIT Kharagpur, from the synergy group and from the related groups at IIT Kharagpur as well as from IIT Gandhinagar. And then we started the option of, we sort of explored the option of having an online symposium, right? And we did not know how it would take off, whether people would be interested, because there are so many distractions online, and what would happen. And I'm very happy to see that it has really come to fruition now. Right, after having 2 online editions, right, we decided to have the first physical edition, right, and even there, right, there's a lot of uncertainty about, is there really an audience, right? There's so many things about machine learning, right? Would we really get funds? Right? There's so many companies that are contributing to so many activities in machine learning, right? I'm very happy to say that both of our suspicions have proved wrong. Right, there's been an overwhelming pouring of applications as well as support from the companies in terms of organizing IndoML. Right, so we are very happy to say that the goal that we initially started out with, which was not really having it's not just about having a conference. There are many different conferences, right? What we wanted to do was that we wanted to have a showcase. But more importantly, we wanted to build a community, right? And I'm sure that these 3 days that we spend out here, right, will be a major step towards that. So with that, I'd like to invite Professor Prashant to inaugurate the symposium.
Good morning, everyone. So I guess 8:30 is still too early to think very seriously, right? No? I hope you all had a good breakfast. It's good to see physically all of you coming to the campus, and I hope many of you will make it again and again to this campus. IIT Gandhinagar has slowly developed its reputation for being very open and inviting to talk about and to do things which are of larger interest. And probably this collaboration between IIT Kharagpur and IIT Gandhinagar to take this initiative is one example of that same thing. As this topic, what you are discussing, is of importance with a lot of responsibility ahead for you, since you are interested in this topic. It is going to affect our lives. Many of people are going to be influenced by what you do in years to come and how things move in that direction. Thinking about science along with its impact on society is where we will be moving, where we will be, you can say, shaping the future tomorrow, you can say. Whatever we do at IIT Gandhinagar, we try to look at both the perspectives at the same time. It is important to develop good science, but at the same time, we need to be aware of what happens as an impact from that. I just want to reiterate that in this meeting also, I hope you will look at the broader perspective of whatever you are discussing about this topic, and also come up with ideas based on what is sustainable, what is for people, what is for the better world tomorrow. As we have 3 days for you on this campus, I'm hoping that you will be able to see around. Especially, you will play a few games in the sports complex. I hope you had a round yet or not yet. Not yet. Some people went. Good. So if you need some special session, let us know. Right? We can probably arrange that. Right? Have a small tournament of IndoML or something like that. Right? So it's very important, as we say here, that you do good work, but at the same time, enjoy life. Equally important for all of us, for our brains to function well in a way, right? I'm hoping also that after going back, you will remember some of your friends that you might have made here in this meeting, and you will collaborate with them. And some of those friends will be from IIT Gandhinagar as well, right? We love working with people all around. And these meetings have the primary purpose of finding those connections, resonating souls, you can say, so that we can start doing better and better by working, augmenting, helping each other, right? I see that there is a unique platform as well as unique format of this event. I have not seen this kind of format anywhere yet. It seems to be working, I guess, or it is under experiment. As we say in IIT Gandhinagar, try things, you will see what works, right? And this format is quite intriguing to me, that is for sure. But at the same time, you as initial participants will have feedback, and I'm hoping that you will convey freely whatever feedback you may have for those sessions. I wish to thank all the speakers who have been able to make it to come here and share with you all the excitements of their work, and also take your constructive criticism on their work to do it even better. With this, I would like to welcome you again, and with the hope that you will have a wonderful, wonderful time in next 3 days. Wish you all the best, and many, many congratulations to my colleagues who have been able to put it together with all the effort. Wish you and them all the best for a wonderful event. Thank you.
Okay, so now it's time for the talks, and I'm very sort of excited to introduce our first speaker of the day, Professor Niloy Ganguly, or Niloy as we lovingly call him. And in this community, in the Indian community, he hardly needs introduction. Niloy is currently the professor of computer science and engineering at IIT Kharagpur. and he has a number of accolades, all these academy memberships and all that. And he's been doing very interesting work on various aspects of social networks, right, as well as deep learning now. So Niloy, I request you to come on stage. Pointer. Yeah. Is this one? Which one? Here. This one is. Everything is mentioned. Hello. You can hear me? Can you hear me? There's some, I think. There's some feedback. Yeah. That first one you are asking. I don't mind. No. Very good. Okay, should I start? Okay, thank you, everyone, for the introduction, and thank you the organizers for inviting me. And this is a work on how to use these. Hello. Oh yeah. Now it moves. Oh. Okay. So thank you, the organizers, for inviting me, and thank you, Anirban, for the introduction. So this is a work on crystalline materials and how to use deep learning in crystalline materials. So the work is done by Kishalay Das. Is he in the auditorium? I think Kishalay Das is around. So Kishalay Das, Vidisha Samanta, Pawan Goel is there, and Dr. Lee, Shatadev Bhattacharya, and me, myself, Niloy Ganguly. So just to give you an idea that like in crystals, there are several properties like band gap, elasticity, and we want to predict the properties of these crystalline materials. And fast and accurate property prediction of crystalline materials is needed because, say, even scientists don't want to synthesize a crystal and then get the property out of it, because that has a lot of cost. So if we can, even before synthesizing the crystal, can predict the property, that would actually cut down a lot of cost. And another thing, what we can see is a crystal looks like a graph. It's a material graph network sort of things, and we can use this sort of graph idea which we have as machine learning people to predict the properties of the crystals. So this is the agenda. So leveraging the power of deep learning framework to learn
robust representation of crystals. How can crystals be represented in a robust way so that we can derive various properties of the crystals? And for crystals, we know that graph-based representations can be a natural choice because crystal has this graph structure around it, and hence we can more specifically try to explore the recent developments of graph neural networks. But what we have to remember that chemical graphs are special category of graphs where we have 3D atomic structures along with bond types, bond distance, atomic chemical property, periodicity, etc., etc. So there are various niches which this chemical graph has. So we want to actually use the graph property, but also have this customization of the graph properties. So just to give you a bit of idea, so this looks like a crystal. If you have, if your school days book, if you think these are crystals, and these are like state properties like final magnetic moment, magnetic ordering, some sort of things. And then there is a lattice property. The crystals are typical lattices, and each lattice may have some weights or some dimensions, and these are dimensions and these are angles. So you have a lattice structure, and you have the atomic coordinates, like this is a NaCl crystal. So we have the atomic coordinates. Just a first level idea how crystals work. Okay, so now just to give you an idea how things work. So density-based functional theory is something which is used to predict properties of crystal. Is an effective tool, but it has substantial computational cost. But this is what is the state of the art, that we use density functional theory to use it. And in recent times, there has been several machine learning techniques. And if you see in the last 5 years, it is slowly picking up crystal property prediction, thus facilitating rapid screening over large material science space. And then there are existing techniques. These machine learning techniques either use handcrafted features, like if you have a SVM sort of things, you have handcrafted features, or you have deep graph neural networks to generate a representation for 3D conformation of crystalline material. So you have an end-to-end learning, or you have a handcrafted features. So let us see what are the limitations. So generating handcrafted features requires specific domain knowledge and human intervention. So that is difficult. And deep learning requires a huge amount of tag data. We know that it requires a huge amount of tag training data. Most of the tag data, and interestingly, most of the tag data which we get about crystals are not like experimental data. They are also theoretically derived from DFT. So keep this in mind. So no experimental data as such. So if the training data by itself has been theoretically derived, there will be a bias. So DFT error bias propagates. So the DFT error bias propagates in current models. And then there is this is per se deep learning problem, but it also comes here that there is a lack of interpretability. So these are the limitations. And what is the opportunity? The opportunity is, although the tag data is less, but there is a large corpus of unlabeled crystal data, just crystals data structure, which can be used to learn the structural and chemical information of the atoms and crystals in an unsupervised way or self-supervised way. So this is there, that you have a little bit of tag data, but you have a lot of untagged data. Untagged information is there. Okay. So keeping this in mind, this is our proposed method. We will see that we have two modules. One is crystal autoencoder, another is crystal explainable property predictor. So we have a crystal autoencoder and we have a crystal explainable property predictor. And what does this crystal autoencoder do? It's an autoencoder based architecture which is trained upon a large amount of unlabeled crystal data, which leads to deep encoding module capturing all the important structural and chemical information. And we have the learned encoding is leveraged with a small amount of property tag data in the CRIS XPP, which is a crystal property explainer, crystal property predictor. So just remember these two things. There is one crystal autoencoder and there is another crystal property predictor. Okay. So keeping in this mind, let me just go through the design slowly a bit. So we have a crystal. So one problem of crystal is has an infinitum. So it's not that the crystal is ending at it is an infinitum. So what we have to somehow encode is one unit of a crystal, whatever that may be, one unit of a crystal. So this is a standard technique, which it's not our invention as such. There has been physicists and chemists who have used this, that if you have a atom, all the other atoms which is within 8 Armstrong radius sphere are neighbors of this atom. So you see, if you think of this pink atom, there are 3 yellow atoms which are neighbor of this pink atom, and here you see that this has 3 links, and each link has some bond feature, 0.25, 1.25, 2.2, etc. So it's, again, you understand, this is like a multi-graph. It's not a single graph that each has one edge. It's a multi-graph, and each edge has some sort of weights. Okay. And then each atom has some features. We have actually 91 features. So just go see. There is group number, period number, electronegativity, covalent radius, etc., etc. So each atom also has some graph feature or has some property. So I guess you have a good idea how a graph looks like. Okay. So now let us talk about the crystal property predictor. So what is a crystal property predictor? It has a crystal graph, and from that crystal graph, through a graph convolution neural network, you have a node embedding. And this node embedding, through an aggregator, you have a graph embedding. And once this graph embedding is there is a multi-layered perceptron. This is just how to classify a property or how to predict a property, and you have the crystal property prediction. Okay. So in essence, what is happening? This is an end-to-end training. From the crystal graph, you give the crystal graph as an input and you get the property as the output. But now let us break this into 2 parts. There is one part which is a graph embedding module, and there is one part which is a property prediction module. So there are 2 parts. One is the graph embedding module and one is the property prediction module. And we always say that deep learning requires a lot of data to be trained. But if we think a little bit deeper, there are 2 modules, and this module, the graph embedding module, requires much more data to train than the property prediction module. The graph embedding module actually requires a lot more data than the property prediction module. So if we have, what is the graph embedding module giving? The graph embedding module is giving a robust graph embedding representation. This is what the graph embedding module is giving. Okay. And if we have a robust graph embedding representation, then property prediction doesn't require a lot of data. It requires much less data. So now, what is the problem? The problem is, we want to have a robust graph embedding, and can we do it without the end-to-end training? So this is the issue. And what can be done if we can transfer? So if we say that this robust representation, that means we have to train the weights of this graph neural network. And if we can get these weights from CrisAE, so if we can get these weights from CrisAE or initialize these weights, not just random weights, but initialize these weights from CrisAE. So this is the idea which we want to bring forward. So now let us go to CrisAE. What is CrisAE? So CrisAE is an autoencoder. So you have an encoding module and a decoding module, and this is trained on a large set of data, and this is a crystal materials project database which has 38,000 crystal data, and you are training the system with this. Okay, and if you think of an autoencoder module, so I guess you know what's an autoencoder. So there is an input and there is an output. The input and output is same. The input and output will be same. Only thing, you are passing this large vector through a small vector, and you are getting the large vector back. So this is, I am abusing many of the terms, but this is in essence what is happening. So when you have this small vector, that means what? That this small vector is capturing all the essential parts of this large vector. This is what is happening. This small vector is essentially capturing all the essential parts of the large vector if it can reconstruct back the large vector. And so if we think of these weights are actually very trained weights which captures the essential properties of the graph or essential properties of the crystal here. And these weights are these weights. Okay. So if we go on training, then these weights will be very trained weights, and it is capturing, it's not a random weight, it's a very trained weight, it is capturing the essential part of the crystal. Okay. And so we have an encoding module and you have a decoding module, and the decoding module does some sort of reconstruction. So we define if which reconstructs, once you have this, you reconstruct the node features. So the node features are like, we have told that there are 91 node features. So when we are decoding, we decode the node features. We decode the edge features, that if there are k edges, what are the strength of each of the edges. I have shown you that there are k edges and strength of each of the edges. We get the strength of each of the edges, and also the graph connectivity, how many edges are there and whether there is an edge or not. So these are the properties we reconstruct back. And in this way, we go on reconstructing and we get a well-trained network. Okay, we get a well-trained network. And once we have this well-trained network, we now transfer these trained parameters to XPP. So now when we are training this XPP end-to-end, this is not randomly initialized. This is already initialized with good data or good weights. This is already initialized with good weights. So now, once you have this good weight initially trained, you can train the entire network with small amount of data, which was the problem of deep learning. We can train on small amount of data. And now just concentrate on this. This is a feature selector. So we built a model, explanatory model, by introducing a feature selector here before the convolution of the node properties. What does the feature selector do? It's a trainable weight vector that selects a weight subset of important node level features. So we have shown that 91 features are there. So all 91 features may not be important to predict a property of interest, say elasticity. Elasticity doesn't need all the 91 features. It may be needing 5 of these 91 features. So here, this feature selector selects only those 5 properties. And so then what happens? As soon as it selects only those 5 properties, you also get an explanation of which properties have really been important in predicting this feature. So we have a model explainability model. And anyway, this is technical. We use lasso regression to impose a sparsity. Okay. So I guess I have been able to make the architecture very clear. And now let us come to the evaluation. So how will we do evaluation? So first is, how effective is the property predictor? So how is the performance of the property predictor, especially when it functions with a small amount of DFT data? That is our essential target, that small amount of data, how it performs. Second is, one problem I said in the beginning is, what is the training data? The training data is also theoretically derived. Training data was not a experimental data. So now when we have the structural encoding, whether the structural encoding helps us to mitigate the noise introduced by DFT calculated property. So this is important, that whether the structural property encodes helps to mitigate the noise introduced by DFT property, and how effective is the explanation. Cross-validate the obtained explanation with domain expert, and we see how effective is the explanation. Fine. So now first property, if you see, we have various things: formation energy, band gap, Fermi energy, magnetic moment, bulk moduli, shear moduli, Poisson ratio, and our is the green. So you see, except for magnetic moment, in all cases, green is the shortest. And shortest is better because what we are showing is absolute error. The lesser the error, the better. The shortest is better. Only here we see that ours is not performing as good as LMNet, because this magnetic moment really doesn't depend upon the structural property. It depends upon some electronics. I'm not a chemist, but when I talk with material scientists and chemists, they say that magnetic moment actually depends upon electronics property and not so much on structural property. That's why we are not being able to capture that. And this is what, when we do on 20% of data, we train on 20% of data and evaluate on 80% of the data. So this is first result. The second result is removal of DFT error bias, which is the most exciting part, I feel. So we consider a property predictor which has been trained with Crystal, whose particular property where we show band gap values has been theoretically derived. So this is what we have done. Now we fine tune the parameters with limited amount of experimental data. So this thing is there. Now we are fine tuning with limited amount of experimental data. So say this is the experiment we do. We collect just 20 experimental instances from domain experts, out of which we randomly pick 10 instances to fine tune the parameters and report the prediction value for the rest. Okay, just 20. So just few short things. 20, 10 we are using to train and 10 for predicting. And here you see, this is the experimental data. Okay, this is the DFT, the original DFT, and this is how our CRIS XPP without being fine-tuned, and this is our CRIS XPP after fine-tuned with 10, just 10 experimental data. See, 0.72, DFT is 0.36, much farther from 0.72 because this is gold standard. Whereas ours without being fine-tuned was 0.9, but as soon as we fine-tune with 10 data, it is coming very, very close to the experimental data. So in essence, so it is not only mitigate, and this pattern you can see always, see 1.12, DFT was 0.85. Ours without being fine-tuning was 0.95. So this is also interesting. See, even without fine-tuning, we are many times performing better than DFT. Why? Because we have done this pre-training. We have done this pre-training with the structural information where there was no bias. Okay. And once we are fine-tuned, it is coming very close to 1.08. Okay. So this is what we are showing, that even DFT or other machine learning models, I have not shown this result. This problem is hugely tackled by this model. And next, when we talk about the explanation through band feature selection, I can show you a case study. Like this is a case study of BA ER2 F8, and there are group numbers, period numbers, electronegativity, and covalent radius, which has been useful for formation energy, which we see that is important. And when we talk with domain expert, they say really these are the important node features which helps predicting the properties. But more importantly, there are each of these differences also makes significance. And I just will explain the electronegativity. So if the electronegativity is different for different atoms, if it's different from different constituent atoms, that gives us stability to the system. And it is known that BA ER2 F8 is stable, and this can be explained through the difference of electronegativity, which we see here. Okay. So to summarize, we propose an explainable property predictor for crystalline materials, okay, with accurate precision using small amount of property tag data. We address the issue of limited crystal data and through a pre-training model. And we further find that the encoder knowledge is extremely useful in debiasing DFT error, and also we provide explanations. Okay. So just to talk about the good things, let us talk about the limitation. So what is the limitation? So one is, see what has happened. This is the CRIS AE autoencoders encoder, and this is the CRIS XPP encoder. So what is the precondition? That both of this needs to be same encoding scheme. So now tomorrow I come with a better encoding scheme. Then I have to redo everything. I have to redo the pre-training. I have to redo the fine-tuning. And so every time I come up with better encoding scheme, I have to do it again and again. And what we know, this is costly. This is costly. So this is costly. So it is like if we come to traditional computer science, every time we do a search, we have to do a sort. So we don't do sort every time we do a search. So it becomes a simple like this. So the point is we have to free these two and not make this tightly coupled. Okay. So this, and there is another point when we have talked about crystal data, there is 38,000 data. So can we use it on more data? And this brings out to the new work, which we will be presenting in AAAI this time. So now we develop a novel pre-trained GNN framework, which is CRISP-GNN, which is trained on much more data. The CRISP or the autoencoder is trained on much more data and more features to design loss. If you remember there, we have taken this edge and graph networks. This was the losses which we are taking. Now we'll take more features to design loss. And once we have done pre-training, instead of just taking that structure to the fine-tuning model, we will do some distillation process. I will tell you what is a distillation process now. Okay. And empirically, when distillation knowledge from our pre-training network, what is our vision? That empirically, whatever may be the SOTA model, whatever the SOTA predictor model, when we do some sort of distillation, the performance will actually improve. So now let us see the autoencoder framework. The autoencoder framework, this is same as the previous part. This is same as the previous part, where we are reconstructing the node features and the edge features. But also we talk with chemists, and material scientists and get some more information. We get the information that each crystal has something which is called space group. Any chemist or chemist here? Or okay, so each material has something called space group, and there are 230 space group, and all crystals can be actually classified under this 230 space group. So this is the space group reconstruction. So we take the space group reconstruction loss, which is an entire graph feature. It is not a node feature or a edge feature, which is an entire graph feature. And then there is another thing which is called crystalline systems. So every crystals can be actually divided into 7 sort of lattice structures, like cubic, monoclinic, okay, hexadronal. So this type of 7 type of lattice structures, and we take a contrastive loss to understand this crystalline system. So now we have node features, edge features, and graph features, everything integrated together. Okay, and the last structure. So now what was the previous structure? This was directly copied here. If you remember, this was directly copied here to initialize. But now what we do, this is a different, and this gives a node embedding. And when we have the crystal property, this also gives a node embedding, and you have a distillation. And ultimately you give the graph embedding. This gives a node embedding, this gives a node embedding, and you have a distillation on MSC loss. Okay. And then from this distillation, this loss is technically, let us think this is the loss. You have a distillation where you take some information from here and some information from here, and you get the graph embedding. So this is directly not interfering with this basic structure. This basic structure can be anything. But when we get the node embedding, we just distill some information from here and put it here. And it is at the embedding layer, and it is not at the graph, at the encoding weights layer. It is just at the embedding layer. So then this becomes, the student model becomes completely independent of the teacher's model. And once we have this, so this is the result. So we take all SOTA model, ALI, GNN, CGCNN, CRISP, XPP, GAD, GNN, and in all the SOTA models. So I would just want to say that ALI, GNN is a much stronger encoding module than CrisXPP. Okay, but even there, when we add this CrisXPP, CrisGNN pre-training, we see there is remarkable improvements. So to summarize, we have built up a huge pre-trained model which can be flexibly used. It can be flexibly used. This is a key point. With any future design of property predictor, an improvement is expected. It's not that what is now, what if in future it comes, this can be plugged in and can be used. And you can get the codes and data from this GitHub, and I think Kishala is somewhere around, so you can meet him and get more information. So thank you, and thank you again for this opportunity. I would be happy to take questions.
Thank you, Professor Ganguly. This is very interesting. It's a very first time I'm actually seeing application of ML to predict properties in crystalline crystals. So I have a couple of questions here. So in one of the slides, you said that you're using 20% of data for training and 80% for cross-validation. Why such a like a lower fraction of data used for training? That's the first question. And a more generic question, second one, which is that you said that you're using that pre-trained weights from based on the structure to predict certain properties. So is it fair to say that this approach is applicable only when the property depends on the structure? If it does not, and in fact, you show that in some properties, it is not working well because it does not depend on the structure. So there's a direct connection between, like, basically the chemist has to tell you that this property is structured and hence we can use this, otherwise we cannot. Is that right understanding?
Yeah. So I will take both of your questions and actually come back to this structure. So I guess one is why you have used 20% and 80%. So this is just to show that we can work on very less amount of data. And the property which I have shown, band gap, that has a lot of data, but there are a lot of properties which doesn't have data. Okay. So for those, this becomes really useful. And the second thing is when I'm transferring these weights, and if it doesn't depend upon the structural property, we are not getting any improvement. And I have shown you one result where their improvement is not there. But now when we have this distillation model, so if the property is not really important, if the structure is not really important, the distillation will automatically not distill anything. So this becomes, not only it frees you from this, gives you flexibility of design, but it also will add some sort of explainability. Oh, see, nothing has been disturbed. Because we have not really done the probing, but as soon as we do the probing, we can show that this is really not giving any information. So that's where this architecture also becomes very versatile.
Thank you.
Hello. So thank you for the great presentation. So this might be a bit of a naive question. A lot of us know a little bit more about AlphaFold, right? Even though it's not chemical properties, right? But these are still molecules, right? So how does like AlphaFold connect to this type of a work, right? How does it compare, or how does it relate to this type of work?
Yeah, I really don't know the structure of AlphaFold, but what I can tell you is that what my feeling is, this pre-training has huge potentials. The pre-training, so just for the students, I want to say, see, when in my childhood, when I was bad in English, I was trying to memorize an entire essay and go to class. That was my technique. I was so I was very good at memorizing. So then my teacher would say, forget about this, just go and read storybooks. So pre-training is some sort of unstructured ideas which you begin to have, and that would help in your structured learning. So it's a very philosophical thing, and I think it's a very important innovation in machine learning, that you just get some unstructured, and all sorts of unstructured ideas are actually good. Talking with friends, going for a tea, hanging around, okay, having a night out, all sorts of unstructured ideas are actually good if it doesn't lead to some sort of catastrophic forgetting. Otherwise, all sorts of unstructured ideas are actually good.
Thank you.
All right. In interest of time, we would move forward.
There's
So-
one more question, but
Okay,
no, I know,
perhaps,
sorry.
Perhaps, sure.
Good morning,
We
sir.
can take one more question. Yeah.
Excuse me. Thanks for the nice presentation, sir. Okay. I want one question. In the pre-training, how much GPU hours were utilized, which servers were deployed, and how much it takes for the pre-training the whole data, data. So
I'm not, somehow the,
So you may keep a mic at some distance. Yes.
am I audible, sir? It's fine. Is it audible? No. I just want to know the implementation data. For example, how many GPU hours it took for the
how many
pre-training?
GPU hours? Yeah, it took a lot. So that's why the idea that we should free this, that every time you have a new model, you shouldn't have a new, means you cannot retrain it again and again. You cannot retrain it again and again. So I have to have Kishalai around here, but around 7 days this take. This takes around 7 days.
Thank you.
Okay. Thanks a lot, Professor Ganguly, for this excellent interdisciplinary talk. On behalf of IndoML organizing committee, we have a small memento for you. Before we move to the next talk, there are a couple of announcements. You can, of course, meet the speakers over lunch, over poster sessions, and they are all organized in the foyer outside, as per the schedule. Second thing is the Wi-Fi passwords are available on the cover page of the notebooks that are given to you along with your kids. If you face any difficulty in accessing the internet, please let one of our volunteers know, and they would be more than happy to help. Moving to the next talk, we have Dr. Monojit Chaudhary with us, who is Principal Data and Applied Scientist at Microsoft Turing, India. He works on building large universal models that form backbone of various Microsoft products. T for title of his talk is T for terrorist, tropical or territorial